So it's been a little while since we've talked about motion, so we are coming back to that now that we have talked about integration. So the first time we did motion was way back when we first learned about how to take a derivative, and then we talked about some different things with that. Now we're going to kind of go in the other direction. So just a real quick reminder before we get too far. What do we remember from long time ago when we first discussed motion? I mean, again, that was back when we did derivatives. So there are three key things you want to make sure that we remember. The first one is that position, or P of t, okay, which is the same thing as x of t. A lot of times we use x of t, and if we're looking at a horizontal position, we've also used various other letters. But basically, anytime you see something like this, we typically mean that that's, you know, our position function, okay? If we differentiate that, we end up with our velocity function, okay? So our velocity function is, again, the derivative of position, and, you know, again, if your position is written as x of t, then x prime of t, again, is the same thing as velocity. If we take the derivative of this, then you end up with acceleration. Acceleration is the first derivative of velocity and the second derivative of position. So all those things that we've talked about in the past in terms of function relationships on concavity, increasing, decreasing, all that good stuff, now all of that can come into play now that we know and can make those connections between the first and second derivative. So again, we start out with position, then you take the derivative and you have your velocity, you take the derivative of that and you have acceleration. If you wanted to go backwards, so if you already have the second derivative and you go back to the first derivative, that's what we're going to get into today, okay? And that's where the integrals are going to come in. So coming up next here, these are just some things that are a little bit of a reminder of stuff we've done in the past. So hopefully this stuff sounds familiar to you. So nothing new yet, okay? So initially means when time t is equal to 0, okay? So initially, whatever time that we're working with, time is equal to 0, okay? At the origin means when x of t is equal to 0. Again, that could be x of t, p of t, z of t if they wanted to, y of t if we're looking at vertical position. Whatever direction your particle is going, when it's at the origin, x of t is equal to 0. At rest is when velocity, v of t, is equal to 0. And let's see, if the velocity of the particle is positive, the particle is moving to the right. If the velocity of the particle is negative, the particle is moving to the left. To find average velocity, let me scroll down here for just a second. Again, if you ever need to pause this to write some of this stuff down, absolutely, that's the beauty of having a video. Pause, write, keep on going. To find average velocity, divide the change in position by the change in time. Again, to find average velocity, divide the change in position by the change in time. How much did you move? How long did it take you? That's going to be your average velocity. Now, your velocity could fluctuate in between because it's a continuous function, but on average, to find out how quickly, or, you know, what your, not your speed, but how quickly you traveled or slowly, divide the change in position by the change in time. Oh, hello, AVT, more on this to come later. Yay, I know you can't wait. Let's see, instantaneous velocity is the velocity at a single moment or instant in time. Okay, so average velocity is your average change in position over time, whereas instantaneous velocity is at any one specific time, what is your rate of change? And okay, that's all for that page. Let's go to the next one. Okay, if x of t represents the position of the particle at x along the x-axis at any time t, then the following statements are true. If the acceleration of the particle is positive, okay, now let's think back to our function relationships information. So acceleration is the derivative of velocity. So if the acceleration is positive, then the velocity is increasing. If on the flip side, if the acceleration is negative, then the velocity is decreasing. Again, this is just your basic first derivative rules. If your first derivative of a function is positive, that means the original function is increasing. If the first derivative is negative, the original function is decreasing. And here I'm referring to the original function as velocity. If velocity and acceleration have the same sign, then speed is increasing. If the velocity and acceleration have different signs, then the speed is decreasing. Okay? A side note here is that there are 4 different ways to use an antiderivative with all the stuff we have going on today. So be very careful on how you do those. And so you're going to practice those up here in just a second. Now, if you don't already have it, if the sub hasn't given it to you, you're going to get the curriculum module for calculus motion, just worksheets 4 and 5. You have already done worksheets 1, 2, and 3. We did that back in derivatives. So now we're doing 4 and 5 with integrals. Again, we're going to kind of talk through these really quickly. You are welcome to pause it at any time if you need to write stuff down. I'll try to explain a few things as we go, but worksheet 4 is going to be pretty straightforward. It's just a bunch of fill in blank. So speed is the absolute value of velocity. This is a concept that you probably recognize from physics. Okay, so velocity can be not only how fast or how slowly are you moving, but also the direction. Speed, because we take the absolute value of velocity, we basically ignore the direction, and we are just strictly speaking about the speed at which you are going, like how fast or how quickly, regardless of direction. If the velocity and acceleration have the same sign, both positive or negative, then speed is increasing. I feel like we just did that on the last slide. I don't think I realized that. That's okay. If they are different in sign or opposite in sign, then speed is decreasing. Actually, it's probably good that we did this because this is something that comes up a lot. So please make sure you understand that when their signs are the same. Ooh, this sounds like a quick quiz question if I've ever heard one. If the signs are the same, then speed is increasing. If velocity and acceleration are opposite in sign, then speed is decreasing. Okay, here are 3 of the ways to use an integral. I know I said that there were 4. Technically, the 4th way is when you use AVT, or average value theorem, with any of these 3 functions. Okay, so let's go through these one at a time real quick here. So this right here is the integral of v of t dt, or velocity, and it's an indefinite integral. We say it's indefinite because it doesn't have any bounds. So when you integrate an indefinite integral, it goes back to a function. Okay, so if you integrate velocity, this will give you the expression for position at time t. Remember, if you differentiate position, you get velocity. So the opposite function, or the opposite mathematical tool, would be to take the integral. So you integrate velocity and you get position. But again, this is an indefinite integral. There are no bounds. So you have to have your plus c, which is your constant of integration, the value of which can be determined if you know position at a particular time. So if they don't give you a particular position, you're just going to end up with p of t plus c. Okay, that's all you're going to end up with when you integrate velocity. So if you look at the very next one, now it's velocity again, but with bounds. So like this, it's kind of hard to see, but this is t1 and t2, so initial time and then terminal time. This is a definite integral, so the answer will be a number. Okay, an indefinite integral, just taking the integral of velocity by itself, will result in a function or an expression with the plus c. A definite integral of velocity is going to result in a specific number. That number is going to be the change in position over time. So when you integrate from time is 1 to time is 2 of your velocity, basically what you're going to end up with is your initial position, your terminal position minus your initial position, which is going to give you your change in position. And they kind of explain that right here. So by the first fundamental theorem of calculus, they don't always call it the first fundamental theorem, but they're referencing that right here. Since v of t is equal to x prime of t, the integral will yield x of t2 minus x of t1. Remember how we do the integral of, normally we go the integral from a to b of f of x, and that results in capital F of b minus capital F of a. Same idea here. The antiderivative of velocity is position, so when you take the antiderivative of velocity, you're going to end up with x of t2 minus x of t1. Okay, another thing for you to make note of, that this is also known as displacement. This is another word that you've probably heard a lot in physics. Okay, so your displacement is basically from time is when you started to the time is when you finish. What is your change in position? Okay, the answer can be positive or negative depending on if the particle lands to the left or to the right of its original starting position. Okay, here's another one here. So now you'll notice this one is very similar. Number 6 is very similar to number 5, but now we've put absolute value bars around velocity. So remember, when we take the antiderivative of velocity, we get position, but also at the same time, the absolute value of velocity is speed. So what the heck is happening here? Because remember, speed doesn't take direction into account. It only just says, you know, how fast or slow a particle is moving. So this is called, or I'm sorry, this is also a definite integral. So the answer will be a number. The number represents the total distance traveled by the particle over the interval. This answer should always be well, I almost said positive, non-negative. It could be 0. Okay, so your answer could be 0 or a positive number, hence why they say it's non-negative. Okay, there's a little note here that I'm going to let you guys read on your own because, well, I know that you're able to do that. But basically, it's explaining to you that, you know, you can have a particle that moves, you know, forwards, then it moves backwards, then it moves forward again. But the total distance traveled would be adding up all of these things, as opposed to displacement, which would only look for the distance between here and here, which we, you know, that would be displacement. We want total distance traveled, so we want to know how far did this particle move. Okay, so what you're going to do next, there are some practice problems for you on worksheet 5. Okay, as with everything we've done in class, I will have the key to this posted on Canvas so that way you can check your work, but please attempt these first on your own. Give them a shot, work your way through them, and then check your answers, okay? With that, at the end of this slideshow, again, I'm going to post this on Canvas. So at the end of this slideshow, there are 1, 2 free response questions, and then some mixed free response multiple choice practice problems, all on Canvas, okay? But basically finish out this whole, finish out worksheet 5 and these practice problems on a separate sheet of notebook paper or on the back of the worksheet module. If there's room, you probably want to use a separate sheet of paper, but your homework / classwork is for you to finish up worksheet 5, check your work, see how you did, and then do those AP practice problems. If you have any questions, as always, Calc Chat is a great resource. Calc View, if you want to look at your book. Off the top of my head, I can't remember what chapter this relates to. I mean, it's chapter 4. Anything we've done with integrals, you'll find in chapter 4. And then always, Prof. Rob Bob or Khan Academy will also have some great resources for you.